Hello everyone, welcome to today's post-contest discussion of Leetcode Weekly Contest 4 to 5. We'll be discussing problems A, B, C, D, right? The thing to notice was that today the last two problems were based on dynamic programming and they were on the standard side. So if you know a bit of DP on trees and if you know normal dynamic programming, you should be able, I think you would be able to solve the contest uh, in entirety. Let's start. Let's not waste time and let's get started. Okay. So guys, let's look at the first problem, which is minimum positive subarray sum. The problem says that you are given an integer array nums and two integers L and R. Your task is to find the minimum sum of a subarray whose size is between L and R and whose sum is greater than 0. Return the minimum sum of such a subarray. If no such subarray exists, return -1. A subarray is a contiguous subarray. Okay. So guys, what does the problem say? The problem says that you are given n and you are given an array. Okay. We need to find the minimum subarray sum. Okay. Such that this sum is greater than 0. Basically, over all subarrays which have a positive sum, what is the minimum possible sum? In this problem, guys, we just have to do what is asked. We can, because of the constraints are here just 100. So what we can do is we can iterate over all the subarrays, generate their sum, and for all the subarrays which have a positive sum, just get the minimum over that. Now the question is, how do you iterate over subarrays? You can set an, like you have two methods. One is an O of n cube method, which is the brute force, which I'll be sharing. And the second thing is the more optimized version. So guys, in the brute force, you select an L, you select an R, you iterate over it, and then you run another for loop from that L to R. After doing this, you can just get the sum between L to R. And if that sum is positive, you can just update some variable. Now, how do you do it in O of n square is something that I would like people to learn. Guys, the thing is that if you look at this particular subarray and if you look at this particular subarray, the difference is only this particular element right here. So we can maintain these subarray sums in a running order. What I mean to say by this, that if you have already computed the sum in this range, if you just add this element, now you have the subarray sum in this range. Now, if you just add this element, you have the subarray sum in this range. You add this element, you have the subarray sum in this range. So if you fix a starting point and you keep adding elements one by one, each of them is going to denote a new subarray. And after this, you just iterate and find the minimum subarray sum of that length. So let me just walk you through the implementation. We start with the starting index. Let me just zoom this further. Okay. Our initial answer is int max, and if in the end we have int max, we return -1, otherwise we return answer. We start with the starting index, basically saying that our subarray should start here. Our sum is initially 0. Sum denotes the sum of the subarray. We iterate from j is equal to I to j smaller than nums dot size. Basically, starting from that starting point, going all the way ahead, we do sum plus equal to numj. Now, another constraint that is given to us, the size of our subarray should be between L to R. So, if j minus I plus 1, what is j minus I plus 1, guys? It is the size of the subarray. If you look at I is equal to j, you will see that the size becomes 1. If j is equal to I plus 1, the size becomes 2, so on and so forth. So if you're given I and j, the size of the subarray or the number of elements is j minus I plus 1. So if j minus I plus 1 is greater than equal to L and j minus I plus 1 is smaller than equal to R, basically the size of the subarray is between L to R, and the sum of this subarray is greater than 0, then we just say that answer is equal to minimum answer comma sum. And in the end, if answer is int max, we return -1, otherwise we return answer. Is this much clear for everyone? Do put a yes in the chat if this is indeed clear. If you have any doubts, feel free to ask me that as well. Just wait for a couple of minutes and then you can move on to the next problem. Ramakrishna says that this is indeed clear, which is amazing. If this much is indeed clear for everyone, let's move on to problem B. Problem B is very, very interesting, and I think it's a very good problem. Rearrange k substrings to form target string. You are given two strings S and T, both of which are anagrams of each other. Your task is to determine whether it's possible to split the string S into k equal size substrings, rearrange the substrings, and concatenate them in any order to create the new string. If it's possible, return true, otherwise return false. So guys, A, B, C, D, C, D, A, B. Okay. S is equal to this string, T is equal to this string, and K right here is equal to 2. So guys, the problem says that you split S into K substrings of equal size. Okay. So since we want to divide it into two substrings of equal size, do you agree this will be the partition? And the first thing to notice is that if we have to partition a string into k equal parts, what is the size of each part, guys? The size of each part is going to be s dot size divided by k. Yes or no? The size of the string is 4. Okay. And you want to divide it into two parts. So the size of each part is going to be 2. Okay. So you can see that this is going to be my first substring. This is going to be my second substring. You can put this AB over here and you can put this CD over here. Okay. And because such an arrangement is possible, we can return true. Otherwise, we can return false. Is this much clear for everyone? Okay, great. So guys, if this much is indeed clear for everyone, let me iterate through one more particular example. Let's look at A, B, C, D, C, D. Okay. And let's look at C, D, A, B, C, D. Okay. Now guys, this is problem S. This is string T. And let's say K here is equal to 3. Okay. Since K is equal to 3, these are the partitions. Now, do you agree, guys? Since these are these size partitions, like each partition is of size 2, the string in T is also made with concatenation of strings of size 2. Yes or no? Yes. So, guys, the only thing we need to check is that we split it. Okay. After splitting it, can we place an AB in T? Basically, is there a chunk AB in T? If there is, amazing, we have already placed it. Okay. Let's say now you have to place CD. You just have to check, is one of the chunks CD or not? Okay. So we can place this right here. After this, you check for the next CD. Can I place a CD over here? If yes, then amazing. Otherwise, false. Is this much clear for everyone? Basically, what we have to check is you have the chunks in S, you have the chunks in T. All you have to do is find a way to place them. And let me ask you one question, guys. If this was CD, AB, CD, till the time you are shuffling the blocks in itself, does it matter? Like it's possible for CD, AB, CD. Similarly, it's possible for CD, CD, AB. Similarly, it's possible for AB, CD, CD. Yes or no, guys? Tell me. Yes. Okay. Now, guys, how do you actually go about checking this? Because if you want to check it in reality, it might be very hard. So, what trick can we use to check this? The thing to notice here, guys, is that the only thing that matters is the frequency of the chunks. Why? Because if the frequency of AB, okay, the frequency of AB chunk in this particular string is equal to 1. Okay. Similarly, the frequency of AB chunk in this particular string is also equal to 1. Does that mean for every AB in S, I can place it at a particular position in T? Yes. Similarly, guys, if you look at CD, the frequency of CD in this particular string is 2. The frequency of CD in this particular string is also 2. So for this chunk as well, since the frequency is the same in S and T, it is possible. So basically for all chunks, the only thing you have to check is that the frequency of the chunks in S is equal to frequency of the chunks in T. And this can be done using a map as you are mentioning in the chat. So is this much clear for everyone? Yes? Okay. If this much is indeed clear for everyone, guys, let me ask you a very simple question. Okay. We know that the size of each particular string is going to be h dot size, okay, divided by k. All right. So do you agree the first chunk is going to be from 0 to h dot size? Let this variable be x. It is going to be from 0 to x minus 1. The second chunk is going to be from x to 2x minus 1. The third chunk is going to be from 2x to 3x minus 1. Yes or no? These are going to be the indices of the chunks. Basically, A, B, C, D, C, D. The left position is going to be 0. The right position is going to be x minus 1. The left position is going to be x. The right position is going to be 2x minus 1. Okay. The left position is going to be 2x. The right position is going to be 3x minus 1. Are the concept of indices also clear for everyone? Amazing. So if this much is also clear for everyone, let me just do this as well. Okay. That is not the case, Ram, because it is given that S length is divisible by K, so you don't need to check for it. So the solution is actually very simple, guys. I've written like a 5-line solution. You have a map of string comma int, and you iterate from I is equal to 0, I smaller than h dot size, and you keep iterating h dot size plus K. Okay. Then you just want to increase the frequency of that particular substring. So it's just string h dot begin plus I, comma h dot begin plus I plus h dot size divided by K. This basically accepts two iterators. One is towards the starting point of your string, and one is towards the next iterator of where you want to end. So our string is going to be from index I to index I plus h dot size by k minus 1. So the indices are going to be from I to I plus h dot size divided by k. So you just do frequency of this substring plus plus, and in the next one in T, you just do frequency of that particular substring minus minus. In the end, you just have to check if all the frequencies are equal to 0, because for every plus you have done here, there should be a minus that has been done here. So you just iterate over your map, and possible and equal to j is equal to 0. Basically, for all the keys inside your frequency, the frequency should be 0. So if that is the case over all possible keys, then you return true, otherwise you return false. Basically, at any point, if j, okay, so you can have a look at the code like this. I think this is more intuitive, and I think this makes sense. Is this much clear for everyone? Ramkrishna says, can we also make the string uh, add plus k times s plus s? This wouldn't work, Ramakrishna, because you will also have to, after you pick them, you'll have to unpick them, right? Like after you place a particular substring, you'll have to remove it from that string because you've already placed it. So you can't check if it exists or it does not exist. Okay, great. So if this much is clear for everyone, guys, let's move on to the next problem, which is problem C. Problem A and B were relatively very simple. I hope they are clear for every one of you all. Let's move on to problem C. So what is problem C? Minimum array sum. You are given an integer array nums and three integers k, op1 and op2. You can perform the following operations in nums. Operation 1 is choose an index and divide nums I by 2, rounding up to the nearest whole number. Okay, and not more than once per index, and choose index I and subtract k from nums I, but if and only if nums I is greater than equal to k. Perform this operation at most op2 times and not more than once per index. Okay, so guys, what does the problem say? Let me just share my other screen. The problem says that you are given an array and of size n, where n is smaller than equal to 200. You are also given op1, you are given op2, and you are given k. You can do two types of iteration. You can do two types of operations. You can do ai is equal to ai divided by 2 seal, actually. Okay, and you can do ai minus equal to k, and this you can only do if ai is greater than equal to k, and this you can do regardless. The constraint is that you can perform one operation, like each operation, only once on each of the indices, and you are given how many operations in total you can perform of each type. You have to find the minimum possible sum of the array after performing all these operations. Is the problem statement clear for everyone? Yes? Tell me, guys. Great. So if this much is clear for everyone, let me just ask you one simple question, guys. Let's isolate one particular element. Okay. Let's say AI. For AI, guys, we have a choice. For every index, we have a choice. Either after performing all operations, AI is going to remain as it is. Basically, we performed no operation on it. Okay. Or AI is going to become AI divided by 2 seal. Otherwise, AI is going to become AI minus K. Otherwise, okay, this is the no operation. This is type 1. Okay, this is type 2. Now, guys, when you are performing both operations, do you agree the order matters? Performing type 1 after type 2 and type 2 after type 1 will give me a different answer. Yes or no? So there are two more choices. You first perform type 1, then perform type 2, then you perform first type 2, and then you perform type 1. So if you look at this, after performing type 1, your answer becomes AI divided by 2, and here it becomes minus K. And here first you perform type 2, so it becomes AI minus K, and then whole divided by 2 seal. So do you agree, guys? These are the only final values you can have for that particular index. Yes or no? For that AI, these are the only values it can have, and that too only if satisfies some constraints, like this AI should be greater than equal to K, this AI divided by 2 should be greater than equal to K, here AI should be greater than equal to K. Yes or no? Tell me, guys. These are the only possible values for a particular AI. Yes? Okay. So if this much is clear for everyone, guys, let me ask you one more thing. Okay. Yes, it is. So guys, on every index, okay, you have a choice. Either you can make it into this, or 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 you can make it into this. But do you agree that we also have op1 and op2? Basically saying that we have to bound the number of type 1 operations we do by op1 and the type 2 operations we do by op2. Yes or no? Tell me, guys. So, can we say that this is just a recursive solution? Let's say we are on index I and currently we have X type 1 operations left and Y type 2 operations left. Okay. If I do nothing, then I will add AI to my answer. Okay. And then I will go to I plus 1 X, Y, because I didn't perform any operations. If I perform the type 1 operation, I'm going to add AI divided by 2 seal to my answer. Okay. And I will go to I plus 1. But now the number of operations of type 1 reduced by 1. Yes or no, guys? It reduced by 1. Now, similarly, I'll just write it over here. If you have X, Y, here XY remains as it is. Here, when you go to the next index, okay, here X reduces by 1, Y remains as it is. Your X remains as it is, Y reduces by 1, and in these both cases, X and Y both reduce by 1. Yes or no, guys? Basically, what you do is at an index I, you fix what you want to do with that element. Like you have 5 choices, you can do that. And after doing that, you go to the next index, which is I plus 1. And when you go to I plus 1, your new values of X and Y are so. Is this much clear for everyone? Like after performing an operation for the next index, the number of operations is going to reduce depending upon which choice you made. Yes or no, guys? Tell me. Okay. Now, guys, the thing to notice here is that on every index, we have 5 choices. So the overall time complexity becomes O of 5 raised to n. But we can just use dynamic programming to memorize this. Basically, what I'm trying to say is that if I give you a particular index I and I give you how many operations you can perform now forward for both of them, the answer is going to remain constant of this no matter what choices you made earlier. If you are on index I and you have X type 1 operations, Y type 2 operations left, the answer is always going to remain constant. So guys, this is all that we have to do. Now tell me one thing, okay? Let's say your recursive function gave you the minimum sum for that particular choice. Okay. This gave you, let's say 10, this gave you 12, this gave you 13, this gave you 15, and this gave you 9. Which one are you going to choose? Tell me, guys. We are going to choose the minimum possible one. Yes or no? If this gives us 9, yes or no? Yes. So we are going to choose the minimum possible one. And this is exactly what we have to do. Let me just show you the code, guys. So before iterating on the code, let me show you what is the dynamic programming solution. dp of I, comma j, comma k represents that we are on index I. There are j type 1 operations left and there are k type 2 operations left. Okay. And this basically stores the minimum sum such that these are the constraints. What is the minimum sum? Such that you're on index I, there are j plus 1 type 1 operations and there are j plus 2, there are k type 2 operations. Okay. And you just have to write recursion. So let me just show you the code of the same. So guys, if j becomes smaller than 0 or k becomes smaller than 0, I'm just returning infinity. You can also do int max or some infinity. If you look at the constraints, the sum of all elements does not exceed 1 is 7. That is why I have set infinity as 1 is 7 plus 1. Otherwise, if I is equal to num dot size, basically if you have performed all the operations, you just return 0. Now, if dpijk is not equal to -1, you return dpijk. Otherwise, these are basically the choices that you make. If you are on index I, you can do nothing. So you can go to index I plus 1 and the number of operations for type 1, type 2 remain the same. And thus your score increases by numsci. If you do only type 1 operation, then you go to I plus 1. The number of type 1 operations reduces by 1. And then your score increases by numsci plus 1 divided by 2. Now you might wonder, why am I doing this numsci plus 1 divided by 2 where it should be ceil numsci by 2? Guys, so there is a mathematical formula, ceil, okay, ceil of A divided by B can be written in integer division as A plus B minus 1 divided by B. Okay, you don't need to call the ceil function. If you know the value of A and B, the ceil can be defined as A plus B minus 1 divided by B. Here B is equal to 2. So A plus 2 minus 1 divided by 2, which is A plus 1 divided by 2. So that is why you will notice that I am using numsci plus 1 divided by 2. For 2, if numsci is greater than equal to k, we saw that the constraint should satisfy. If numsci is greater than equal to k, then your answer is going to be this much. Otherwise, it's going to be int max. For 1 comma 2, uh, these are going like your answer is going to be k plus, if this is greater than equal to 0, then it's going to be I plus 1, j minus 1, k minus 1, because you are performing 1 and then 2. So the number of type 1 operations reduces by 1, the type 2 operations reduces by 1, and your final value is numsci plus 1 divided by 2 minus k. Because you perform the type 1 operation, the value becomes numsci plus 1 divided by 2, and then it reduces by k. Otherwise, it's int max. And here, if numsci greater than equal to k, then you go to I plus 1, this remains as it is. Numsci plus k minus 1 divided by 2, because first your value becomes numsci minus k and then it becomes divided by 2, otherwise int max. Your dpijk is just minimum of nothing, comma 1, comma 2, comma 1, 2, comma 2, 1. And in the end, your final sub problem is that you start at index 0, you have op1 number of type 1 operations left, and you have op2 number of type 2 operations left. A very simple 10 liner, 5 liner, whatever you want to call it, dynamic programming recursive solution. Is this much clear for everyone? We just do recursion and we want to memorize this because there can be overlapping sub problems, which will bring down our time complexity from 5 raised to n to O of n cube. Yes. Do have a look at the solution, guys, and let me know if you have any doubts. Aviraj says last two conditions. Aviraj, 1, 2 and 2, 1 means that you are going to perform the type 1 operation first, and then you are going to perform the type 2 operation. So if you perform the type 1 operation first, your value numsci becomes numsci plus 1 divided by 2, right? And after that, you perform the type 2 operation on this. So that is why it reduces by k. And for 2, 1, you perform the type 2 operation first. So numsci becomes numsci minus k. And then that value you are performing the type 1 operation on. So that becomes numsci minus k divided by 2 ceil. So that is why you can see. Okay. Anshul says that why can't we use heap to solve problems? You'll have to prove, Anshul, because there are a lot of choices. How you can't really make sure if choosing one choice is going to be more optimal than the other. Like if you do prove it, amazing, but it can be solved very simply without much thought using dynamic programming. You know the choices you have, and you know that the constraints allow this particular solution. So you can just solve it using dynamic programming. If there is a heap solution, you can feel free to add it in the chat. We'll look at it later. Okay. Okay. Guys, let me know if this solution is also clear for every one of y'all. If it is indeed clear, we'll move on to problem D. Okay, so I'll just wait for a couple of minutes. Do have a look at the code and let me know. Yeah, I'm not sure either if greedy is going to work. Like if there is a good proof of if it works, then fine. But otherwise, it seems unlikely for me. Amazing. Is this problem and solution clear for every one of you guys? Tell me. Amazing. So if this much is clear for everyone, let's move on to problem D, which is maximum sum of weights after edge removals. Okay, let's have a look at that. There exists an undirected tree with n nodes numbered 0 to n minus 1. You are given a 2D integer array edges of length n minus 1, where edges I is equal to ui, vi, wi, such that it indicates that there are nodes between ui and vi with weight wi. You have to remove some edges such that each node has an edge with at most k other nodes. Okay. The sum of the weights of the remaining edges is maximized. Okay. So what does the problem say, guys? The problem says that we are given a tree. Okay. This is 4. This is 2. This is, what is this? This is 12 and 6. Okay. 12 and 6. All right. We are also given a k. Your k is 2. What this means is that in your final tree, okay, or final forest, each node should be connected to at most k other nodes. Here you can see that this right here is connected to 3 uh, edges. So we'll have to remove one of the edges, right? And similarly, we have to make this constraint solvable for every other node. Basically, it should hold for every other node. So we have to remove the edges in such a way. Okay, so basically, if we remove this particular edge, you can see that the constraint is satisfied, because if you remove this edge, okay, this is connected to 2 nodes, this is connected to 1, this is connected to 1, this is connected to 1, and this is connected to 1. So the constraints are satisfied, and this is the maximum sum of edges. Like over all possible ways to do it, the sum of the edges that are remaining is maximum. This is basically 22. So this is what the problem asks. Remove the edges in such a way that the remaining edges have maximum sum. Is this much clear for everyone? 1 second, guys. Okay, great. Is the problem statement clear? Okay. Now, guys, the thing is that if you look at this problem as it is, okay, like if you are like you want to remove the edges and do something like that, you will notice that for a node, you can remove edges in upward direction as well as in downward direction. Yes or no? So there is no kind of direction to this problem. Like if you wanted to do a sort of DFS call, you can't really do it, because depending upon whether you are removing the parent node or not, the answer for this will change, the answer for this will change. So we need to bring some clarity into this problem. That is, if we want to solve it, we want to solve it in one particular direction, because otherwise for each node you can solve it in any form, right? So we need to bring some uniformity, and that is what we are going to do. Guys, for a particular node, okay, what are we going to do? In these tree problems, it is very common, like this is a very common idea. We would like to, okay guys, if you say that we have already solved it for this subtree, we have already solved it for this subtree, and we have already solved it for this subtree. Do you agree? Then we can decide which edges do we want to keep here, yes or no? Yes? Tell me guys, like if you find the maximum edge sum after removing some edges in this subtree, then you find it after removing some edges in this particular subtree, and after that you find it after removing some edges in this particular subtree. Then let's say you introduce their parent, and now you want to decide which edges you can add such that the constraint is satisfied, and after solving it for this node, we can then solve it for all of its children and then solve it for the tree. Basically, we want to solve this in a bottom up fashion. Okay, because if we can solve it recursively for the children, then we can solve it for the parent. Yes. So guys, but there is a small issue with this, and let me show you the issue. Okay, if you solve it, okay, if you solve it here, like for this particular tree, let me just draw this tree. Okay, let's say the edge weights were 12, 2, 6, and then this is 4. Guys, do you agree when you and k is equal to 2 here? Okay, in this subtree it's already satisfied, you don't need to do anything. In this subtree it's already satisfied, you don't need to do anything. In this particular subtree, do you agree it's already satisfied? So you don't need to do anything. The cumulative answer for this subtree is 8. Okay. But, and here also you don't need to do anything. But guys, when you come towards solving it here, basically you want to add some edges here. Can you notice that it's more optimal to have this edge and remove this edge over here so that the constraints are satisfied, rather than having this edge and not having this edge? Do you see what is the problem here? Yes? Tell me guys. Do you see why we would face problems if we just wanted to solve it top down using DFS? Like the choices we make might not be optimal. Okay. But guys, we can do a very simple thing. Okay. For a given node, okay, we know that it has some number of elements. Okay. Let's say it has X nodes connected to it. Okay. Or basically X edges. Out of these X edges, guys, we have to remove max of 0, comma, X minus K edges. Basically, if X is smaller than equal to K, it will be 0. Otherwise, if X is greater than K, then we have to remove X minus K edges. All right. Now, guys, let's assume we are doing a DFS call. Do you agree, as I showed you, it matters whether this edge has been removed or not, depending upon, let's say this is the parent and we are doing DFS in this direction. Depending upon whether we have removed this parent edge or not, the choice that we make here would change. Because if we have removed this edge, then we have to remove one less edge over here. Basically, let's say k is equal to 3. If we do not remove this edge, we will have to remove all 3 edges over here. But if we do remove this edge, we only have to remove 2 edges over here. Do you guys agree that these are the only things that mattered? Yes? Tell me, guys. Okay. Shubham says, please one more time. Shubham, see, for this parent, okay, let's say you made some choice. Let's say you removed this edge. Now, depending upon if you removed this edge or not, do you agree the choices for these edges would change? If you chose this edge and k is equal to 3, you will have to remove only 2 out of these 3 edges. But let's say you don't remove this edge, then you'll have to remove all 3 of these edges. Yes or no? This is the only difference when we choose or not choose the parent to node edge. Correct? Okay. So guys, do you agree? For every node, we need to compute 2 things. What is the maximum answer in the subtree where the parent to node edge has been removed? Okay. And what is the answer in the subtree where the parent to node edge not removed? And if we are able to do this, we will be able to come up with a dynamic programming solution. Basically, we can say that dp of I comma j represents the maximum answer in the subtree of I, such that if j is equal to 1, we can say that the parent edge node has been removed. Otherwise, if j is equal to 0, we can say that the parent edge node has not been removed. Is this much clear for everyone? I'll be elaborating on how you can calculate things and everything else further. But is this much clear for everyone? Okay, great. If this much is clear for everyone, guys, let's look at something. For a given node, okay, sure. Let's say we have to remove x edges, okay. For every node, you know what is the answer if you do remove, if you don't remove this, and what is the answer if you do remove this, okay. This is when you don't remove, okay. This is when you do remove. All right. Now, each of these child, this is for child 1, this is child 2, x2 and y2. Okay. Now, guys, let me do it for only 2 and then I will generalize further. This has x1 answer if you do not remove this edge. This has y1 answer if you do not remove this edge. This has x1 answer if you do not remove the x2 answer if you do not remove the edge, and y2 answer if you do remove the edge. Okay. Now, guys, we have, let's say k here is equal to 1. This is the only tree. So do you agree we'll have to remove either this edge or we'll have to remove this edge? Yes or no? And consider the weight has been considered over here. Okay. Like if the weight is chosen, it's included in x1. So guys, if you remove this edge, your answer is going to be y1 plus x2. Okay. And if you remove this edge, your answer is going to be x2 plus y1. Correct? Do you agree, guys? We have to choose maximum of y1 plus x2 comma x2 plus y1. Basically, over all the choice, we'll choose the most optimal one, which maximizes our answer. Correct? Yes or no? Tell me, guys. Yes. So, guys, let's assume that x2 plus y1 is greater than x1 plus y2. What does this imply, guys? This implies that x2 minus y2 is greater than x1 minus y1. Yes or no, guys? Tell me. We chose to keep the edge connected to x2 where x2 minus y2 is greater than x1 minus y1. Is this much clear for everyone? Basically, what this means in general words or layman terms is that this is when you don't remove it, and this is when you remove it. The difference minus them should be as large as possible, and that is when you'll keep that edge. Or in other words, if you have to remove uh, capital X nodes, you are going to remove those capital X edges which have the smallest x1 minus y1. Yes or no? If you have 3 children with x1 comma y1, the second child has x2 comma y2. Okay, the third one is x3 comma y3. All right, let's say you have to remove two of them. You are going to remove the ones with the smallest value of xi minus yi. Let's say these two have the smallest two values of xi minus yi. So you will choose to remove the node edges connected to these two nodes. Is this much clear, guys? Like if you have two nodes, you'll pick the one with the smaller xi minus yi to remove that edge. So you can just say that you can sort these values based upon xi minus yi, and you would want to remove those edges which, okay, just give me 1 second, Shan. I'll get back to your answer. Okay, just give me 1 second. Okay, now that is all that you have to do, guys. If you know your answer, if you keep that edge, and if you know the answer, if you remove that edge, you find the answer for all children. Okay, and after that you just sort these values based on xi minus yi, and mathematically you can compute how many edges you have to remove. Okay, basically dp of ij represents the max answer. After that, your number of edges you have to remove is adjacency I dot size, okay, minus 1. Okay, if j is 1, you will have to remove one less edge, okay, minus k. Because if you have already removed this particular edge, then you have to remove one less edge, otherwise you have to remove one more edge. Does this make sense for y'all? This is the number of edges you have to remove. After doing this, you more or less on this I node, you solve it for each children. Okay, either you do remove the edge, you do not remove the edge. Let's say the value is xi comma yi, and after that you solve it for each of the nodes, and after that you just sort it and you pick the ones with the smallest xi minus yi value. Nikhil says not able to understand the equation you wrote. Nikhil, here, if okay, let's say this is 0, this is, let's say this edge value is 3, this edge value is 4. Okay, let me just take a very quick example, share what I meant by this. Okay, this edge value is 3, this edge value is 4. If you're solving for this node, okay, if you do not remove this edge, the answer for this subtree is going to be 3. If you do remove that edge, the answer is going to be 0. Okay, now similarly, if you do not remove this edge, the answer is going to be 4. And if you do remove it, the answer is going to be 0. But this is because there is nothing below it. But let's say there was something below it. Let's say there was a 5 here and there was another 5 here. So then this would have become 8. Okay. And this would have become 5. This would have become 9. And this would have become 5. Okay. Now, let me just write it more simply. So 8 comma 5. And after that, you have 9 comma 5. Right. Now, guys, we have to make a choice. Let's say k is equal to 1 here. We have to remove either this edge or this edge. If you remove this edge, this particular edge, okay, if you remove the first edge, your answer is going to be 5 plus 9. The answer for not removing this edge plus removing this edge. But if you remove this edge, your answer is going to be 5 plus 8. You would want to pick up the answer which gives you the maximum 1. And if you look at it in terms of equations, you want to pick up maximum x2 plus y1 comma x2 sorry, this is x1 plus y2. Okay. After this, you want to pick up the one with the larger x2 plus y1 or the larger xi plus the other yi. If you just switch this, it becomes, if this is larger than this, then x2 minus y2 is going to become larger than x1 minus y1. So it is more optimal to choose the values with the smaller xi minus yi. This is nothing but it's called an exchange argument. Okay. If you guys weren't able to come up with this particular solution, you should look at exchange argument. Exchange argument is basically coming up with these inequalities that you come up with, and then you just have to solve it as it is. Let me just show you the solution. All right. So you have your adjacency list. You make your adjacency list. You have dp of ij, where I denotes if you have the node or not. Like I denotes the node, j denotes if you have taken the parent edge or not. Okay. If dp ij not equal to -1, you return dp ij. Your operations to do is maximum of 0, comma adjacency dot I dot size minus k minus j. These are the operations you have to perform, and this is the answer. Guys, so here you have two choices. Either you are going to keep this edge or you are not going to take this edge. So after you do take this edge, your answer is solve for the subtree. Okay. And your weight increases by weight of the edge. You notice that I'm keeping a 0 here because for the next node, we have not removed its parent node edge. But if we do not take this edge, the answer increases by, you go to the child, your j becomes 1 because you did remove that edge, and your parent is I, and then you go to self. Children dot pushback take comma not take. After this, we are just sorting the children based on L dot first minus L dot second smaller than right dot first minus right dot second. And after that, you iterate over children dot size. And if I smaller than equal to ops to do, basically we want to remove the first ops to do elements dot second. Basically, we want to remove the edges of the first ops to do nodes, right? So for the first ops to do nodes, you select the dot second value, because dot second value means not taking that edge. And after that, for the rest of the elements, you just pick up the maximum child I dot first comma child I dot second. Basically, for the other k other values, you are free to choose any of them, which is dot first or dot second. And in the end, you just return dpij's answer. This is a dynamic programming on trees solution. It is a very standard solution. This is something that we teach in TLE level 4. Okay. So if you do want to learn it, you can consider TLE 12.0. Apart from that, I hope you enjoyed the post-contest discussion. It was a very concise explanation of all the problems along with the intuition. Okay. All that you need to do for this is exchange argument. Now getting on to some of the Q&A. Okay. Getting to the questions. Shan says my rating is 1867 but couldn't solve 3. You should practice dynamic programming, Shan. The third problem is a very classical dynamic programming problem. So you need to figure out what choices you have and do that. Shubham says, what is exchange argument? Exchange argument, Shubham, is this. You saw that picking up a value with smaller xi minus yi is more optimal. So over an array, the value with the smaller xi minus yi is always going to be more optimal. Basically, what is the condition on which you sort the elements? That is known as the exchange argument. Okay. Is TLE. This is the proof, Aviral. This right here is the proof. Okay. Is TLE 12.0 live? Yes, Nikhil. TLE 12.0 is live. You can definitely check out our website and do by the level which is comfortable for you. Okay. Shan says, sir, would you like to suggest something to increase CF rating? It depends on what your rating is, but I would suggest practice. I think that is unsaid. Read more editorials, read more editorials. That is one of the most underrated things that people don't do. Second thing is Upsolve. And last but not the least, you should actively learn new topics. Not a lot, but like you should do a 60-40 or 70-30 split where 30 time you're learning new topics and 70% you're solving randomly. Okay. Ram says, what rating question did they ask in rubric interview? You can say from 1800 to 2100 code forces rating problem, Ram, and they were around advanced graphs and tree problems, right? You can look at CSES and look at the later half of graphs, trees, and dynamic programming. Those are the type of problems. Shubham says, just one more thing. Why don't you go from top node to children and just remove the edges? No, Shubham, it won't work. Why won't it work? That's exactly what I told you. Okay. If you look at this, okay. If you look at this tree, and let's say k is equal to 2 here. Here you have three choices. Either you can remove this, or you can remove this, or you can remove this. And let's say this is your tree. If you removed this right here, you don't need to remove any other edge. But if you removed this edge right here, you will have to remove one of these two edges. Similarly, if you removed this edge, you'll have to remove these two edges. So the choice that you make alters the choice in the particular subtree. And that is why we cannot do a greedy solution over here. Okay, Shubham. Where should I practice the sorting inequality question? You can go to progvar.fun. Okay. You can go to progvar. 1 second. You can go to progvar. 1 second, guys. You can go to progvar.fun. And in progvar.fun, you can go to greedy. I think math. And in math, you can go to I think exchange argument should be here. Like if I just put in exchange, yeah, you can see that exchange argument is here. Okay, guys. So I guess that is more or less it for the solution. I hope you guys enjoyed today's discussion. Thanks a lot for watching. See you guys next time. Do like if you did enjoy. See you guys next time. Till then, bye bye.